Okay, so let's start. Good afternoon. Welcome to one of our Spring into STEM mini lectures from UCL Engineering. Today we'll be talking about inkjet printing, which is not the 45-pound printer on your desktop, which goes bad after 6 months, but Dr. Rafael Castrejon-Pita will tell us how inkjet printing is now a cutting-edge manufacturing tool of the future. An interesting topic. We're just going to wait a couple of minutes for others to join, and Dr. Castrejon-Pita will take questions after his short lecture, which should 15 to 20 minutes maximum, and then you'll be able to ask questions. If you have questions throughout, just type them into the Q&A function at the bottom of your screen, somewhere near the bottom left of the screen, and just type them in there, and Rafa will do his best to answer them. He's an expert on the subject, so I'm sure he will be capable. Okay, that's about it for now. We're just going to give them other participants another couple of minutes to pile in, and then Dr. Castrejon-Pita will take it away. I'm going to go offline now, and looking forward to hearing all about this inkjet printing. So over to you, Rafa.
Thank you, Michael. Can I just confirm that you guys see my presentation, Michael? Anyway,
we can see it. It's full screen.
Thank you so much. Thank you very much for the introduction, Michael. As you did say, let us take just another minute for others to join. I will be very happy to take any question at the end, and please use the Q&A link at the bottom of your control page on Zoom. And let us start in 1 minute, please. Thank you very much for joining. My name is Rafael. I am an associate professor in manufacturing, innovation, and enterprise at UCL, part of the mechanical engineering department. So 30 seconds more for others to join. Thank you so much for connecting. Thank you very much for joining. This is inkjet printing, a manufacturing technique of the future. We begin in 20 seconds. Okay, guys, let us start. So this is inkjet printing, a manufacturing technique of the future. And I'm going to start by saying that, as Michael said right at the introduction, this is not really about conventional inkjet printing. This is definitely not the case. So we're looking at industrial inkjet systems, and modern industrial inkjet systems can print much faster than conventional technologies. So they can now print out a few meters per second, single pass, so that you don't have to go back and forth. And these are applications for the printing of newspaper, advertising, and very, very importantly, packaging. So as you can see, this is any supermarket in the UK, Europe, or any of the developed world will have packaging for every single object, for every single product. And it's simply because of regulations. So regulations state that some information needs to be provided in all the products, from expiry dates, the contents, the place of origin, and, for example, allergens. And actually, the market is so big now, the inkjet printing market is so big that it's now larger than consumer electronics, which practically means that you spend more money on printing products than on home electronics. And packaging is here to stay. But the thing is that inkjet printing is now trying to expand into a different market, from the printing of electronics to the printing of cells, for example, to create organs, to replace medical technologies such as sprays. Inkjet printing is also trying to displace conventional technologies such as spray coating for painting applications. And of course, there are tons of applications and potential applications on the 3D printing. This is how Inkjet works. What we see is a series of droplets being jetted by a printhead. So the printhead is at the top, and we see individual droplets. They are normally in the 50 micron in size. They are very fast. They can travel up to 10 to 20 meters per second. And what is very amazing is the fact that you have repetition rates up to 10,000 droplets per second. So I'm just going to repeat that fact because it's quite amazing. So now we have the technology to print very small droplets, 50 microns in size, very quickly at the rate of 10,000 droplets per second. What we see here is the jetting. So you have a very long filament which breaks up into smaller droplets, and these droplets are the ones that produce the patterns. And from them, you can create 3D objects or graphics. What is also very important in inkjet printing is that each of these nozzles can be controlled digitally. So you have full control over which ones fire, which ones don't fire. This printhead is from SAR, it's a UK company, and they now produce a 3D printer where you can, for example, print the glue on a bed of particles or from the ink, build objects in 3D. So there is a massive market on 3D printing these days. If we were to divide the stages of inkjet printing, what you have is the ink, which is ejected from the nozzle. Then it forms a jet. Then you have the breakup. So the jet breaks up from the liquid reservoir, and then you have a jet. Then the jet coalesces into a single droplet, and then that droplet eventually lands. So what is very interesting is that this is a very open problem in physics and engineering. So we do a lot of research trying to increase the resolution of inkjet or expand the applicability of inkjet, the compatibility of inks. More on that in a second. So this is an actual inkjet printer, which we see at the top, jetting droplets. I insist they are very, very small. And as you can see, you have the substrate coming left to right. And it is through the jetting of these droplets that you form your image or your graphics. Inkjet printing is really good at printing ink, but the idea is that a lot of companies are now investing in research as to expand the use of inkjet printing into, for example, the printing of metals, glass, glue, complex fluids, biological fluids, let's say cells or blood, and many more. In fact, the dynamics of droplets are also very interesting from the point of view of physics and fundamental research. And the reason is very simple. We also find droplets in a lot of other natural processes. For example, if you were to see how the jet on your shower breaks, it will happen something like this. So you have a jet, then the jet develops a surface instability, and the surface instability eventually breaks up the droplet. So this is exactly what you see by high-speed imaging on a shower. We also see droplets in natural processes. So this lizard in northern Texas and the south of Mexico produces these jets as a defense mechanism. Of course, we know that the anglerfish hunts the prey by using a jet and droplets. And of course, as I say, in several applications in engineering, such as sprays and aerosols, we have droplets being produced by a jet and to produce coatings. We also see droplets impacting objects, such as a pool of liquid on splashing. So when it rains, mist is produced by the jetting of these smaller droplets called satellites from splashing. And of course, the icing on airplane wings start by depositing droplets on the fuselage. So there is a lot of interesting topics in here. As I say, one of the stages is the breakup of liquids. So this is actually high-speed imaging of a dripping drop from a tap. And we have studied this by ultra high-speed cameras. This actually video shows the recording at 250,000 frames per second. And what we found is that the breakup is self-similar, meaning that regardless of where the droplet breaks off from the jet, the angle formed by the cone of the filament is equal. Regardless of the conditions, it is universal. So this is really good for setting or validating numerical models. We also study, of course, the deposition of droplets, because that determines the resolution of inkjet printing, and of course the color registry. So this is a droplet landing on another droplet of different color, and this is a droplet landing on the side of the droplet. And of course, this is really good for studying color registry. So if you're printing colors, you need to know whether there is a very good definition between the colors. We also use these experiments to validate numerical simulations, and in here we see a collaboration with the University of Leeds, in which they develop lattice-Boltzmann methods to validate our experiments and their simulations. So we have a one-to-one set of experiments. We're also interested in how droplets coalesce with pools of liquids. And of course, there are plenty of industrial applications where this happens. So any industry where you need to transfer a liquid to another place, it will be done through jets and droplets. So in this case, we see a droplet landing on a liquid that is moving from left to right. And of course, if you have the wrong conditions, you will either have a splashing, as the one we see at the screen. And if you're not careful, you deposit a droplet, and the droplet doesn't coalesce, and the droplet will simply surf forever on the droplet, on the pool. And of course, if you optimize the conditions, what you find are a very small combination of conditions where you actually have very good mixing. And of course, this is deciding in applications where you are looking for a fast mixing, or for example, if you are combining two components, you wish to get a very fast reaction, you need to find these conditions. Droplets also, of course, we have all experienced rain on our fabrics. So we also have collaborations with, for example, DFTL. This is the Defense Science and Technology Lab in the UK, where they are interested in the penetration of droplets through fabrics. For example, you wish to repel droplets. That means that if this is your mesh, you don't wish for the droplets to pass through the fabric. You wish for the droplets to keep on one side of the fabric. And these are just some experiments, again, using high-speed cameras. We can see that regardless of what you put on the fabric, so these are two different coatings, they are supposed to be non-wettable coatings. And as you can see, regardless of the coating you put on, if the speed of the impact conditions are right, you always have penetration. So I am trying to say that if you wish to develop something that is quite permeable, that is non-wettable, you kind of need to do a lot of research. Now that we have passed COVID, as you know from the news, viruses and other illness are passed by droplets, so tiny droplets that are ejected by the mouth. We need to be very careful as to prevent splashing, because, well, of course, you wish, I mean, in the case you have droplets, you wish the droplets to stay on a substrate, not to break up into smaller droplets and then transmit the disease absolutely everywhere. So we have done a lot of research on the splashing of droplets. So where, for example, if you have on the case at the top, you have water impacting a glass, but if you put a hydrophilic substrate, you have something non-wettable, what you see is, well, bouncing, but first of all, you have a splashing. And of course, the impact depends on the liquid properties as well. So while water doesn't splash, ethanol under the same conditions of speed will definitely splash. So we have done a lot of research on splashing, and now we know that splashing depends on the liquid properties, but also on the wettability of the substrate. So for example, this is an impact on a superhydrophobic surface, which is a non-wettable, so something like Teflon. So you have the impact, but eventually the droplet simply bounces off the surface. So again, there will be applications where you decide one or the other. So some applications where you would like a very nice spreading, such as inkjet printing, but there will be other applications where you probably don't need or don't wish to have the droplets stick on your surface. So having super hydrophobic surfaces is an advantage. We also use droplets to create biomaterials. So biomaterials where you can put cells and the cells will happily live. And this is great for example, skin applications where you need to grow skin on a substrate and then transplant those into a patient. We have created a mode in which we can use inkjet printing to create a different shape. And what we have done is actually later on put cells on them, and we have actually checked that the cells are happy to live in these materials. So this is a kind of a 3D printing, but for biomaterials. And this is the way we do it. So we jet one droplet on the top of the other one. We have done with peptides, we have done it with alginate. So these two liquids, the liquid at the pool and the liquid at the droplet, they react chemically and form a soft solid or a solid that can actually have different mechanical and chemical properties. Okay, so now is the time for me to say that if you wish to get involved, if you are a student looking for a place or looking for the next stage in your career, we can say that UCL is now expanding from Bloomsbury to the east, and we are offering mechanical engineering is offering 2 new programs. They are MSCs in manufacturing with innovation and enterprise, and the MSc in future manufacturing and nanoscale engineering. So these programs will have a project, and in that project, well, actually there are 2 projects. There is the group project and the individual project. And in these projects, you will have the opportunity to work with an academic. You will have the opportunity to interact with industry. You will have, the MSc will provide you with technical and manufacturing and enterprise business skills, mostly focused on manufacturing. And there is another webinar next week in which the presenter will cover the MSc in future manufacturing and nanoscale engineering. Our MSc in manufacturing, innovation, and enterprise will have compulsory modules such as the fundamentals of engineering. They will have entrepreneurial finance, master entrepreneurship, and advanced characterization. And you will have the opportunity to work in a very in a state-of-the-art lab with the state-of-the-art facilities. It's a new campus. There are also optional modules in which you will have advanced computer applications in engineering, material design for manufacturing, precision manufacturing, or sustainability analysis. And finally, you will have 90 credits out of 180 on projects. So you will have an individual project and you will have a group project. It will be based at UCL East, where you will have access to modern laboratory facilities offered by the Manufacturing Futures Lab. This is the building here. It's brand new. It's going to be open practically next month. And you will have the opportunity to collaborate with world leader academics. And at the programs, you will have career programs. You will have employee-led events, so interaction with industry, interaction with business, and access to a lot of industrial experience through the projects. What can I say? If you have any interest, please look at the MSc in manufacturing with innovation and enterprise, and I will be very happy to take any questions you might have. This is the new site of UCL. So there is a big building called Pool 1, and then the Future Manufacturing Lab right here. Thank you so much. I will be very happy to take any question, and I'm now going to take a look at the Q&A. I'm just going to stop sharing. So let us see. Michael, did you hear me?
Yeah.
Okay, so we have 19 participants. I will be very happy to take any question now. If you can use the Q&A link on your Zoom control. Thank you. So the question is, can you give us a few more examples of cell printing and its applications? Oh, thank you, absolutely. So the reason we are developing these applications is to, for example, print organs. So we have to start from the basics. So it's not only about printing the cells. We have done successfully the printing of skin cells. We actually have a startup from our research. but it's mostly about not only the printing of organs, but also about, for example, studying organoids. So in which you print a cell on a substrate, let it grow, they form a mini organ, and you can do a lot of research, including Alzheimer and Parkinson disease. There is another question. What are some of its applications in medical science? Yeah, I mean, as I say, a lot of groups in the world are looking for the printing of organs. That's definitely the aim for the future. Diljoy, thank you so much for your question. How long is the course at UCL? It's an MSc. And at the moment, we are accepting applications from any engineering program. So as long as you have the interest in this link between innovation, enterprise, and manufacturing, we'll be very happy to take your application. Now, what are the legit subjects? I mean, as I say, you have a background in physics, engineering, maths, and you have an interest in manufacturing, hands-on experience. This program is probably something you need to take a look at. Most of the information is available online, and I look forward to seeing your applications. Thank you. So how do mechanical engineers work in the industry? Well, at least in the UK, to keep the products, for example, an inkjet printer competitive in the market, you need to do a lot of research and development. So for example, if you wish to increase, for example, the resolution of inkjet printing, you have to do a lot of experiments. In some cases, we do a lot of collaborations with industry aiming to, for example, perform numerical simulations or to do empirical studies. There is definitely a lot of interest, at least in the UK and Europe, on engineers for further product development. So there is definitely a lot of interest in the subject. Happy to take more questions. Yeah, the program
Hi.
is this October.
Oh, no, carry on. I was going to answer one of the questions, but carry on.
Yeah, I mean, it's about the MSc program. So the program starts this October, but applications are now open and they close by mid-June.
Yes, I was just going to answer one question, which may have been about undergraduate programs. So our undergraduate programs in mechanical engineering, there is two versions. One is, well, three versions. One is a 3-year BEng degree, and there's another, and there are two 4-year degrees. So that's integrated masters, call them MEng degrees. For all three of those, I think the standards are, in A-level terms, it's A star AA, and math and physics are essential. You can also have a year in industry as a replacement, I think, for your third year. I need to double check that. But there are also students who go out on placements for a whole year, and there is the opportunity to study in another university for one of your years.
I'm going to add that we also take undergraduate student projects in the lab. So as an undergraduate degree student, you will also have the opportunity to work with an academic and do research in your last year. Krishna, thank you for your question. Yeah, definitely. So because inkjet printing is digital, you can control what goes into which layer. And there is something called grayscale technology, in which you can actually print different depths, layer by layer. And of course, you have to think that it is not only a single printhead, but in a conventional printer, you will have a collection of printheads. Each printhead will handle a different color or a different ink or a different liquid. So you could, in principle, control very precisely the composition of individual layers, all down to microns. Thank you, Krishna. Okay, if there is no further questions, thank you very much for connecting, guys, and I will be very happy to answer any of your questions on email. So my email is seen in the last, well, let me put it back on the screen. So r.pita@ucl.ac.uk. So very happy to answer any of your questions. Michael?
Okay, thank you very much. I was just busily scampering around for a link to our YouTube channel. If you want to learn more about mechanical engineering, obviously you can visit our website, which I'll just place in the chat. That will give you a link to all our programs, including these new ones at UCL East. But if you're thinking about an undergraduate degree, the competition is fierce, I have to warn you. Then have a look at our site here. And you can have a look, if you want to get a flavor of life at mechanical engineering, you can have a look at our YouTube channel, which is linked from the front page. So left only, therefore, let's just double check if there's any more questions. Okay, that's all the questions we've got. Left for me just to thank Dr. Castrejon-Pita, and thank you for attending this Spring into STEM lecture. There are many more lectures. If you check on UCL Engineering's website, that's UCL Engineering, not UCL Mechanical Engineering, there are many more lectures coming up over the next few weeks, and I would encourage you to dip in and and you might learn something really useful, but also it might give you an indication of a path you might go academically. So thank you very much for attending our webinar, and we'll see you soon. Bye.
Thank you, guys.